Good afternoon and welcome to the concurrent session number 10 on biofuels, hydrogen and other sustainable technology, current situation and alternative scenarios. I'm Antonio Gerascitano and work at AIEE, the company of the GS Group carrying out research in the energy sector. Before starting with our session, I would like to thank you, the Italian Association of Energy Economists, SDA Bocconi School of Management, as well as the conference organizers for this appreciated invitation as a chair of this concurrent session. As reported in the program, there are 3 speakers. Therefore, in order to be on time with the scheduled program, each speaker has about 25 minutes for the presentation. At the end of each presentation, there will be 5 minutes space for question and answer eventually. So the audience, including the panelists, can send the question writing through the Q&A chat. As well known, the European Commission's adopted a package of proposal to cut greenhouse gas emissions by at least 55% by 2030, compared with 1990 levels in order to reach climate neutrality in 2050. So green economy is the pillar for researching this goal. Indeed, in this concurrent session, our speakers are going to illustrate their research activity on this topic. Let's start with the first speaker. It's my pleasure to introduce Amasalu World-Yellow. He is currently a Marie Curie Research Fellow at Ca' Foscari University of Venice. He holds a PhD in economics from the University of Technische Universität Dresden. Previously, he worked as postdoctoral researcher at Potsdam Institute for Climate Impact Research in Germany. He is interested in the interlinkage between the environment, energy, and economy, and serves as editorial board member and referee for several peer-reviewed journals. In addition, he is also a member of the European Association of Environmental and Resources Economists, International Water Resource Association, German Alliance for Global Health Research. He's going to present a work entitled Energy, Economic and Environmental Accounting for Biomass Fuels in Ethiopia. Amasalu, the floor is yours. Thank you very much.
Yeah. Thank you very much for the wonderful introduction, and good afternoon from my side to all of you from Venice. Could you see the slides now well?
I can't see it.
Can you see the slides, or do I need to share?
No.
No, you cannot see. Okay. Not yet?
Okay, now we can see it.
Okay.
Thank you.
Thank you very much. So the topic is already introduced by our colleague, and I'm so grateful for him for the wonderful introduction. And I will briefly introduce the topic as well as also the situation in the country, and also followed by the materials and methods, and also brief discussion on the results, and finally the conclusions. So Ethiopia is the second most populous country in Africa, with an estimated total population of 115 million, but only less than 25% of the total population lives in urban areas. So it's basically a rural country. 75 to 80% of the population lives in rural areas, largely depending on agriculture. And it's also a typical low-income country with less than $1,000 per annum. And therefore, this economic and demographic structure of the country is also reflected in the total energy system or overall energy system. Therefore, the country has one of the lowest per capita energy supply. For example, it's 1/6 of the total the per capita energy supply in Italy, or 1/5 of the energy supply of the world average. And it's also Ethiopia has also one of the least diversified energy systems, even by African standard. and it's ranked 101 out of 108 countries in terms of its ability to provide sustainable energy. And one of the main, or of course not, the total energy supply is actually overwhelmingly dominated by the biomass fuels. That's why I'm also focusing on the biomass fuels in this presentation. As you can see, it was about 95% in the year 2000, and about now 88%. And but it will also remain as a main source of energy in the country, even by the mid of the century, as it will remain more than 52%. And not only this, about 93% of the households in the country depend on biomass fuels like agricultural wastes and also fuel wood for their cooking activities. And that's why it's very important to look at the nexus between biomass fuels or biomass energy and the environment, and as well as the biomass fuels and SDGs. And biomass fuels are really, strongly linked with the environment, as they contribute to deforestation. Evidence show that 1/3 of the total fuel wood in the country comes from unsustainable extraction of forests and woodlands. And it's also the main contributor for greenhouse gas emissions related to the land use and land use change sector. It contributes to indoor air pollution, which is actually responsible for 5% of the total disease burden in the country. And it compromises soil nutrients, especially as we extract mostly or removing agricultural wastes like crop residues and animal dung for fuel would compromise soil nutrients, which could lower agricultural crop production by about 2%, and even agricultural GDP by about 7%. Therefore, you can see that the biomass energy is has implications with several SDGs, including the human health or the SDG 3 or climate action, that's SDG 30, SDG 2, which is related to promoting sustainable agriculture and food security, and SDG 15, which is sustainable management of the forests or woodlands. And of course, it's highly linked with SDG 7 as is related to energy. So biomass fuels represent a clear case where energy consumption is strongly linked with the environment and the economy, particularly in Ethiopia, where they are the main source of energy. Most of the households depend on biomass fuel, traditional stoves, which contributes or amplifies the emission, and smallholder agriculture is the main source of livelihood and even exporters. Therefore, the main objective of this presentation or this work is to estimate the energy, economic, and environmental emissions from the stationary combustion of solid biomass fuels in Ethiopia, and the paper seeks to contribute to the policy debate on energy-related environmental and economic issues and also SDGs in the country. So coming to the materials and methods, I look into include the four main solid biomass fuels in the country, which are firewood, charcoal, crop residues, and animal dung. And consumers are the households and services, both commercial and public institutions, but of course, they have insignificant share of the total consumption. And I focus on the year 2015-16, the Ethiopian fiscal year, because of data availability. So the mass of the biomass fuel combusted in that specific year comes from different reports, very specific to the biomass fuels, and also extracted from different energy balance statistics. And also I try to also make own estimates from two estimates or reports on fuel wood as well as on agricultural wastes. And the emission factors are based on IPC guidelines, and the net calorific or the lower heating values are from greenhouse gas protocol database, and I multiply using retail prices from the Central Statistics Agency of the country. So I summarized here the method in general. So the starting point is the mass of the combusted fuel of the four fuels that I mentioned. And that can be then converted to, or that would be the starting point to calculate or to compute the energy equivalent, which is depending on the net calorific value of each fuel combusted, and the economic values or the economic contributions are calculated or based on the retail prices. And on the left side, we also calculate the emissions of greenhouse gas emissions as well as particulate matters based on the emission factors, again, to multiply on the mass or the weight of combusted fuels. And lastly, it is also forest degradation or deforestation, which is calculated as, in this case, I only depend on the firewood consumption to be divided by the biomass stock, above ground biomass stock per hectare of land. So the results are also summarized, just following the same structure with the methods. And as you can see, the total of the 4 solid biomass combusted in the country in 2015/16 was about range, depending on different data sources, range from 95 to 125 million tons, and which generates energy equivalent to from 33,000 to 44,000 kilotons of equivalent. And this, the economic contribution of biomass fuels is estimated from 4.2 to 7.7% of the total national GDP in that specific year. And the emissions are estimated from 165 to 200, nearly 220 million tons of carbon equivalent. And the deforestation is estimated to be around 500,000 hectares. So further notice on the results or further look at the results show that about 99% of the total biomass fuels are consumed by the householders. It's not a surprise, as I've tried to mention in in one of my first slides. About 80% of the population lives in rural areas, therefore they mostly use the biomass fuels. And also biomass fuel supply, I mean, if we look at specifically on the specific fuels, firewood accounts from 62 to 76%, again, depending on the data sources of the total biomass fuel consumption. And the results reported here, especially on the economic and the energy contributions, are also comparable to some previous studies. Whereas the greenhouse gas emission estimates here are a bit higher, not a bit, I mean, by far higher than the estimates, even, for example, in the national determined contribution of the country. Basically, the main difference of the results for the greenhouse gas emissions is, of course, because here we apply the emissions from stationary combustion of the fuels, unlike the national determined contribution or any other greenhouse gas inventory, which is based on net removals of biomass stocks. And the effects on forests and comparing the deforestation or the forest degradation calculated here with national deforestation statistics shows that mostly the fuel wood might be collected through forest degradation. It may result forest degradation rather than involving cutting standing trees. So it would be better to term it as forest degradation, rather forest or woodland degradation, rather than saying deforestation. So coming to the conclusions, biomass fuels have substantial role in the Ethiopian energy system, but they have very also profound implications to the quality of the environment and human health. And therefore, concrete actions are required to increase the household's access and use of cooking stoves, better or modern cooking stoves, and also access and use of cleaner cooking fuels like biogas or bioethanol, where the country has also very huge potential. And it's also in parallel important to keep to scale up afforestation, reforestation, and agroforestry activities. Therefore, the extraction, the fuel wood extraction would still remain below the sustainable yield of the forests, the sustainable biomass yield. So the study contributes to accounting and modeling energy system in line with the system of environmental and economic accounting, the UN and specifically with the energy sector. And it also helps, it also contributes to the discussion adds to the discussion on E3 or energy economy and environment nexus framework. And future research, which specifically applies or depends on country and fuel specific emission factors, and also linking this or trying to link the health consequences of this indoor air pollution estimate here may be important. Finally, I want to say also what is on the funding. This is part of the work of MENT, as also mentioned previously, as it is also a Marie Curie research project. I thank you all, and I welcome any questions. Thank you.
Thank you very much for your presentation. We have just appreciated your study, which links biomass energy with the economy and environment. That can be a certain step for future research aimed at accounting and modeling the Ethiopia energy system in line with the E3 nexus approaches. I don't know if someone has questions for our speaker. We can try to check the Q&A chat. No, let's continue with the second speaker. I'm so glad to introduce Professor David Chiaramonti. He is a full professor of systems for energy and environment at the Polytechnic of Turin, Department of Energy. He is president of Record, no-profit research organization based in Florence. He works on thermochemical and biochemical conversion of biomass. In addition, he authored more than 118 publications on international journals, conference proceedings, and edited books. Moreover, he's member of the international organization such as the European Biomass Conference and Exhibitions. Professor Chiaramonti has been country representative of AIEA Bioenergy and today country representative at the International Civil Aviation Organization Committee for Aviation Environmental Protection, Alternative Fuels Task Force. He is involved in various European Commission projects on sustainable aviation fuels. He provides scientific coordination to the industrial platform alternatives and renewable transport fuel forms. In this conference section, Professor Chiaramonti is going to present a work which is entitled Liquid Alternative Fuels for Transport Decarbonization, meeting the Fit for 55 goals. I'll give the floor to Professor Chiaramonti. Thank you very much.
Thank you very much, Antonio. Good afternoon, everybody. Yeah, my speech is about the alternative fuel sector and the challenges that we have had in this moment. So, summarizing the technological status of the market, the critical elements or bottlenecks, and some consideration about the policy that is being developed in these days in Europe, and then obviously following that in the member states. I will focus mostly on civil and maritime sectors because they are key, crucial for carbon emission reduction, but they mostly rely only on a fuel change, a fuel switch in the system, as these are very difficult to electrify or hard to abate sectors. So the liquid alternative fuels are going to play a major role for still quite some times in this area, at least. That's a clear priority for the Commission, for the European Union, but also for international organizations at global level. We have a number of packages impacting of this sector, from the well-known RED to other that indirectly but heavily impact on this, like the ETS scheme, the offsetting programs and the various policy measures and so on, the taxation directive, the infrastructure directive, and so on. So it's a package of initiatives that have to be in some way addressed. But overall, these sectors have a very peculiar characteristic. They are global, they're international. So differently from passenger cars, here we have to deal with international organizations like ICAO for aviation and IMO for maritime that really regulate the market and the decarbonization process. So as I said, in Europe, we have many legislative measures like the Green Deal, of course, the Climate Target Plan, the RED in particular, which are specific section on maritime and aviation, the ETS scheme, which is also part of the package, and it's matter of discussion also offsetting CO2, also of the ICAO Corsia program. And more recently, in the Fit for 55 package, we have the Refuel Aviation that we go through very quickly. There's a very transparent message that aviation and maritime are priority for the European Union. This was done already in RED 2 through the introduction of multipliers 1.2 for no food and feed-based feedstock for aviation and maritime fuels. And then there are a number of certification schemes. Well, technically speaking, the sector is very, very complex and vary a lot. Despite that, the option until 2030 are very few, as I will come back to this in a moment. But technically speaking, we can produce even very sophisticated fuels like jet from a number of biomasses, from lipids, of course, but also from lignocellulosic, algae, wastes, and so on. All this process goes through a value chain, which is comprised by feedstock production and collection or recovery processing, sometimes intermediate energy carrier, processing into a final product, and then deployment this in the end user. Today on aviation, we have already a number of certified fuels, AIEE certified fuel. This is the current set of technologies that are eligible for use in aviation. With on the last column, you see the blending limit that is allowed for each of these chain, from Fischer-Tropsch to HEFA to synthesized isoparaffins, alcohol to jet, algae, and co-processing in conventional refineries, which is up to 5% of the total. These routes are quite complex to be developed. It is time and cost-consuming process. Today, the TRL, technology readiness level, and FRL, fuel readiness level, focuses on HEFA by vast majority. I mean, either processed fatty acid S and free fatty acid, that is the lipid-derived jet fuel. That is indeed the dominant fuel. The biojet that is used in commercial flights today is exclusively this. And personally, I don't expect a large-scale production of different types of fuels from other type of feedstock within a time frame to 2030, 2035, unless in pilot demo first-of-a-kind plants, but not large mass-scale production. Also, hydrogen is an option, also electricity, but quite in a medium to long-term time frame. Surely after 2035. E-fuels is slightly different. They could be developed in a shorter period. There's a significant issue with cost on that area. Cost to produce, as I say, the most challenging fuel, that is the jet, for the chemical and physical characteristics of the product has to be fed to commercial flights. But in principle, I mean, producing hydrogen from renewable electricity and from this converting CO2 into a number of products normally called PTL, this is doable from a technical point of view. Today, the vast majority of the installed capacity is given by HEFA, the lipid-based jet fuel. We have Neste, Total, Sky Energy, UPM, ENI dominating this area, and we don't expect this will change very soon. The legitimate question is, do we have enough feedstock? Considering the Fit for 55 target of 5% of renewable fuel in aviation, which means roughly 3 million ton oil of biojet for European conditions. Is doable. I mean, we could assign, let's say, sufficient biomass to cover this 5% of jet. So, given also the fact that while on one hand we don't expect the alternative fuel for road sector to really decrease, but however there would be the addition of other alternative fuels like electricity in transport, and that is an advantage for the passenger car sector and for road sector as a whole. Indeed, creating a demand also adds some pressure to the feedstock side to produce significant volumes of product. And this, in principle, could create some critical situations in the agricultural part in particular. We do not see big issue until 2030, but it could be for the 2050 targets. So it's absolutely due to develop other process routes from lignocellulosic and waste, for example, that are using abundant raw material, normally at low or even negative cost. Nevertheless, in that area, we do have quite considerable capital investments cost and also operational expenditure. So there are still industrial development route to be done there. Expected soft demand, the soft demand is expected to ramp up. We carried out a meta-analysis with JRC, the Joint Research Center of the European Commission, right before the pandemic, and it was clear that aviation and maritime are the one with multipliers approximately tenfold times. Indeed, there was the pandemic that impacted very heavily on the jet fuel market, but still there are already signs of recovery. Now we are in the middle of maybe another pandemic wave that could indeed impact on air transport and traffic, but on average we already see a sign of recovery. The volumes expected are in the range of 1 to 3.4 million ton oil equivalent. This depends on the level of support that we assign to that, which correspond from 1.5 to 5.6% of the expected demand. Costs and prices are different depending on the use of biomass or waste, but indeed we are much higher than the fossil fuel as it is today. This was an analysis carried out again before the pandemic. It's not yet been updated to my knowledge, but I think it's necessary the moment the pandemic is passing away. I mean, we need to reanalyze this cost, because in the meantime, producers are working to develop supply chain of sustainable feedstock to feed this product. Future cost trajectories are not easy to forecast. There's a possibility to integrate with biofuel plants that already exist. There's need for R&D and technological improvements. There's the learn by doing effect and economies of scale. So one could expect some cost reduction between 5 to 27% in terms of capex and opex. But also financing costs could be a positive element if reduced to bring some other cost reduction opportunity between 5 and 16%. Well, for those interested here, the price model provides a cost structure of biofuel production from HEFA, the lipid-based route to 2050. In any case, you still see that there is a significant feedstock component for HEFA and slightly less for alcohol to jet. As I said again before the pandemic, the fossil jet fuel production price rise stays in a figure around 600 euro per ton. And again, here you see how the different options place versus this fossil jet reference price. They're all involved some much higher. There are ranges because they depends a lot on the local conditions, feedstock supply chain, economy of scale. The RFNBO is what we normally in non-technical areas we are called power to liquid or e-fuels. So these RFNBO are the renewable fuel of non-biological origin, where the energy to produce the fuel comes from non-biological sources, namely PV and wind. Again, here you see the same thing. Moving to the conclusion, the sector, as the entire fuel sector, is clearly a policy-driven sector. So policy is needed, not necessarily in terms of direct support, but in terms of market regulation, as well as in its barrier removal, also non-technical barriers. The two areas of maritime and aviation looks very different in terms of technical specification of fuels that can be used, but also in terms of cost and revenues. So they need a separate analysis. Some countries, that's what we want also to develop for Italy, have made estimation on route maps to the South market. That's Dutch estimates. One can agree or disagree on that, on some of these estimates. Some looks a bit optimistic, some others very realistic. In case they will happen a bit later on rather than sooner. It depends also on the volume of the demand, which indeed for some countries much higher, and in the local condition. As said, the policy options are covering various elements of the value chain. They can choose different elements to attack the issue, like the supply side or the demand side, the volume-based or CO2 intensity approach, and the scope if we are moving in internal to EU aviation or international. International is regulated by ICAO, as said. There is a ramp up that is estimated, as I said, up to 2050 with RFNBO that in principle after 2035 could really provide a contribution in significant amount to the sector. The Refuel Aviation, which is in the Fit for 55 package, is describing some of these policy options, discussing this, and clearly this is matter of negotiation in Brussels in this year and in the next year. Clearly, all these options, I don't go through this, but all these options have different impacts on the jet fuel price. Different policy option determines different biofuel price. So the cost goes hand in hand with the policy, as I said here. You see that, for example, the increase of ticket price is estimated based on some modeling normally used at European level to estimate these scenarios. And so you see that the ticket price increase, depending on the different scenarios, goes from a few fraction of a percentage to up to 8% maximum 2050, depending on the volume. So technologies, concluding, are moving ahead. There's need to upscale and to support investment. There's need for stable regulation and standardization. There's need to implement a European clearinghouse assisting operators developing renewable fuels in this sector, and strengthening the collaboration between the stakeholders, which includes mostly the fuel producers, the institution, the fuel users, the infrastructure like the airports, and the research organization. With this, I thank you very much, and I'm here in case of any questions. Thank you.
Thank you very much, Professor Chiaramonti. You have just shown liquid alternative fuels for transport decarbonization in order to meet the 55 goals. So, which is the policy scenario and how this impact on market penetration and costs?
Well, I think that we have to distinguish between the 2030 to 2035 timeframe and the post 2030, 2035 to 2050. Developing new technologies is already ongoing, but scaling this up, and with scale up, I do not mean simply to build it bigger, but to replicate in many units. We consume some 70 to 80 million ton oil equivalent of jet fuel. So to see an impact, you will need a lot of these plants. So we don't expect any significant change to 2030, 2035. The HEFA will dominate. So in this time frame, the supply of sustainable lipid will be the keywords and the difficult. And in fact, most of the fuel operators are investing in agro-industrial projects to develop sustainable lipids. Post 2030, 2035, lignocellulosic and e-fuels will come into the scene, I'm pretty sure. Costs will be reduced compared to today. Plant will be industrialized, scaled up. And in that case, then a massive amount of fuel could be produced from this feedstock. And probably that will be the moment that will ramp up at large scale.
Thank you very much. The last but not least speaker is Luc Bucky. He is a mechanical and welding engineer. Currently, he is a manager of network technical services at SNAM. Since 2012, he has been chairman of the technical committee design of the European Pipeline Research Group. Currently, he is involved in certification of the hydrogen readiness of SNAM pipelines. Up to 2010, he was manager of the SNAM laboratories, destructive and non-destructive testing of steels and coating. Since 2011, Dr. Bucky has been in charge of the integrity management of SNAM pipelines. For this energy symposium, he's going to present a work entitled Hydrogen Pipelines, Not a New Issue, the SNAM Experience. Dr. Bucky, the floor is yours. Thank you.
Thank you. I hope you can see it.
Yes, we confirm.
Okay. So thank you, Mr. Chairman, for your presentation, and good afternoon to everybody. It's a pleasure to be part of this event today. And first of all, let me thank my colleagues Gianpaolo Annoni and Marino Crespi, who are together with me the authors of these papers. So H2 pipelines, they are not a new issue. I will show you the SNAM experience. I like closing a presentation with a question session, but I also like to start a presentation with questions. So I have some questions for me today. I hope I can answer. Why we are speaking today about hydrogen, and why specifically in Europe? And then we move, of course, why hydrogen in Italy. And as the chairman has already presented, I am mechanical engineer. I work every day on steel, so my presentation will be especially focused to answer two questions. Can we build today new steel pipelines to transmit in Europe hydrogen? And can we use the already existing pipelines to transmit hydrogen? So let's start very briefly from the first question. We know very well that there is the goal net zero emission that we want to reach by 2050. So hydrogen can have an important role as green energy. Green hydrogen is becoming more and more competitive. Green hydrogen produced from the renewable resources. This is because the cost of the renewables is changing rapidly, and there are many improvements in the technology for green hydrogen. Green hydrogen can be also competitive with fossil fuels in many applications. And if we think to the industry with high thermal energy consumption, like refineries, steel mills, and so on, also blue hydrogen can be used to decrease the time to reduce the emission of CO2. And last but not least, hydrogen can be also used for heavy transport, of course, electricity production and heating. And what about Europe? So we understand that hydrogen is an important green solution for energy, but there is an important point that we have not to forget. This is a map of the gas transmission network that is already operating in Europe. Is a very complex asset that is working. You can find a lot of maps. This one is published in internet from the ENTSO, the European Network of Transmission Operators for Gas. And the important point is that most of these existing pipelines can be rehabilitated from natural gas through hydrogen transmission. That means that on one hand, you have hydrogen, that is the new vector. On the other hand, you already have an asset that can be used to transport this vector. There are many works already available. Some of them are showing that the required investment in order to convert the whole chain of the network for gas transmission, natural gas transmission through hydrogen is a cost between 10% and 25% respect to the cost for building a new dedicated asset for the energy. And why are we speaking about Italy? Okay, I show you this is today the SNAM pipelines network that is composed by more than 32,000 kilometers of operating pipelines. Nowadays, our network is the largest and the most interconnected gas network in Europe. We receive in Italy gas from North Africa, in Sicily. We receive gas from the North Sea, from North Italy. We receive gas from Russia. We receive gas from the new interconnection of TAP, and we receive also gas by ships with different LNG entry points. If we look to Italy, it has also, let me say, a natural role of bridge between North Africa and Europe. That means that in case that North Africa will be able to produce green hydrogen from solar sources or from windmills, we already have an asset that can be used to move this energy to Italy and to Europe. I told you that I work every day on steel, so a few data. The network is nowadays composed by pipeline that have a maximum diameter of 56 inches. We are operating them with a maximum internal pressure of 75 bar, and we are using a very common steel grades for gas transmission that is, according to IPFL standards, the grade X65. So, something about this asset and the readiness of this asset to be used with hydrogen. First of all, let me say that it's more than 100 years that carbon steel has been used for transportation and storage of hydrogen, so it's not something new. And nowadays, there are more than 1,500 kilometers of hydrogen pipelines that are operating. So we can say that the use of carbon steam pipelines is not a new issue. Not only is not a new issue, but there is already a technical standard from the American Society of Mechanical Engineering, the technical code ASME 3112, that is already published, and it gives technical rules both for the design of new hydrogen pipelines and the rehabilitation of existing pipelines. According to this standard, you can apply the rules if you are transporting with your pipelines pure hydrogen, that means 100% in volume of hydrogen, but also blend gases from 10% of hydrogen and the other part of natural gas. Something about this technical standard. It can be applied between 10% and 100% of hydrogen. It can be applied to a maximum steel grade of X80, that is steel with 555 megapascal of field strength. It's very technical, but let me say it's higher than the one that we are using normally in Italy. And this is important because higher is the steel grade and more restrictive are the requirements that the standard impose. The requirements are imposed because, of course, we want to consider the potential effects that can be arise because we are introducing hydrogen on the steel that is different from natural gas. And what is the logic on which is based the whole standard? Of course, it imposes requirements in order to avoid that because of hydrogen, there are different issues on your pipeline. Let me say that at the end, with the application of the standard, you can assure the same level of safety and reliability of the asset that we are currently using with natural gas. That means that, of course, we don't want to change the probability of failure of the asset because we are changing the gas. The technical standard gives two main criteria in order to guarantee these levels of safety of the integrity of the asset that are called option A and option B. I go quickly through both of them. So the first option is option A. Let me summarize that the main stress that there is on a pipeline, on each single pipe, is that is an offshore pipe used for gas transmission, is due to internal pressure and is proportional to the pressure and to the diameter and is inversely proportional to the thickness. And if we guarantee a low level of circumferential stress, hydrogen has not any effect on the material itself. So according to this technical standard, if you keep a low level of pressure, you don't have to add any new requirements to your steel pipelines. This is the option A. More complex is option B. According to option B, you can keep the same level of maximum pressure that you are using today with natural gas. That means that you have a maximum circumferential stress that is the 72% of the yield stress. But you have to verify some, let's say, mechanical behavior of the steel in hydrogen environment. That is, at the end, something that you can do with some tests of the material toughness in hydrogen. So there are many studies that are going nowadays, if you look for them, because this is a standard that was born, but not related to big and complex network, but just to short pipelines. And so in some points, it's also very conservative. And now we want to apply it to big pipelines. And there are many studies for this. Another important point that this is an American technical standard. So in Europe, we are working for a European standard because we need of it. And especially there are a lot of works in order to find the best way to apply the option B to the existing pipeline, because I mentioned before that according to the option B, you can keep high pressure, but you have to test the materials. Of course, if your material is already operating, we have to find a reliable way to demonstrate that we can test all the materials that are already operating, so are already underground. So what is doing specifically SNAM on this point? Let's speak about two cases, new pipelines and the existing one. For the new pipelines, we have already changed our internal technical standards. That means that nowadays, if we buy pipes for building new pipelines, we are already buying them according to the ASME B3112 option B. That means that at the end are pipes that can be used at the same pressure that we are using with natural gas. This summer, we bought the first kilometers, more than 400 of pipes with these characteristics. They were produced in Greece by Colin Pipeworks. They are pipeline with a diameter of 26 inches and thicknesses of 11 and 50 millimeters. So we can use this pipe to carry hydrogen up to 75 bar of maximum internal pressure. These are some pictures of the specific testing that we did for that. And it's testing in order to verify the high level of toughness of the steel in a hydrogen environment. We also start to characterize all the existing pipelines, the 32,000 kilometers I mentioned before. It means that we can quickly verify the readiness of this asset according to option A. So we are collecting all the characteristics and we are comparing the requirements with option A of this American code. So at the moment, almost the entire network, we are already verified according to this option. And the results is that is compatible with the transport of hydrogen. Even if in some cases that is something between 25 and 30% of the total length, if we want to transmit hydrogen, just using this option, we have to reduce the maximum pressure of the pipeline. This process we are doing by ourselves initially, and now we are involving also a third-party certification body. RINA is working with us, and it's certifying this process of characterization of the maximum pressure that we can use on all of the already existing pipelines if we put hydrogen. That's not all, because of course we want to characterize also according to option B the existing pipelines. That means to demonstrate where we can use the maximum pressure without any reduction. So we are starting some tests. We are starting to cut from the field, from the operating pipelines, some pipes to do test laboratories with hydrogen. And we are demonstrating that the level of toughness is the one required from ASME. I don't have many results for you today. We can dedicate a more technical session on this point. So the conclusion, all around the world, hydrogen is already transmitted also with pipeline. So the use of carbon steel pipelines is not a new issue. There are already technical standards that give requirements to build or to rehabilitate to hydrogen existing pipelines. Their ASME code, the American technical standard, is already available. There are many groups of works that are working in order to build also new guidelines and European standard for this topic. So that's all. Thank you for your attention.
Thank you very much for your interesting presentation. So we have appreciated the SNAMEC experience on this topic. In addition, you mentioned in your presentation that a European technical standard is expected for hydrogen pipelines. So can you tell us something more about this topic?
Yes, nowadays in Europe there is a technical standard, is the EN 1594, is related to natural gas transmission. It's not including hydrogen. So there is not, in this moment in Europe, a technical standard with the requirements for hydrogen transmission. This standard is under vote for a new revision. It will be published after the vote, of course, at the beginning of the next year. And this revision is already including an informative annex with the rules for new pipelines and conversion of existing ones. In this first revision, we are expecting that the standard will link to the ASME code, to the American national standard. But we are expecting that in the next years, a European standard focused on hydrogen will be published. We are working a lot between all the TSOs in Europe and also inside the European Pipeline Research Group. There are many activities. Normally, the European Pipeline Research Groups, where there are both pipe mills and TSO, do a lot of research on steels and pipes, and the results are normally used by the European committees to produce new standard. In particular, we are doing some full-scale tests. That means that we are testing in accelerated way some pipelines, both new and both old pipelines that we have cut from the real networks, in order to demonstrate the requirements that we want to put in this European standard.
Thank you very much. I think this session is over, and I would like to thank you again, all the speakers, for their contribution, and all attendees. Have a nice continuation of the virtual conference, and have a nice evening. Thank you very much.
Thank you.
Thank you. Good evening. Bye-bye.
Have a good evening.